Hello, class. Sorry, I didn't have my headset on. Hope that is at the right location now. Let me just double check that. Yes, I am recording. All right. Today, what I want to do is I want to look at the angle of friction or the angle of repose. And this sort of goes along with the last, angle of repose. This goes along with our last lecture that we had, along with friction and the inclined plane. And when we look, I'm just going to draw a figure over here. And this time I'm not going to make it 30 degrees. I'm just going to make it an arbitrary angle, right? Whatever that angle is, we're just going to call it theta. And then I'm going to put, a box or whatever, some type of weight source on there, and we're going to look at the components of that weight force, because we're going to have one that's normal, right, to that, which would be W sub n, and we're going to have one that is tangential to that, which we'll call W sub t, just like we did before. All right, so I want to talk about just under these conditions, right? We don't have any tension on a rope that's pulling it up or holding it or whatever. Nothing like that. Just under those conditions, what would the angle be dependent upon the coefficient of static friction? So when will that start to move, right? The angle for movement. And of course, by movement, I mean moving down the thing. I'm gonna eventually, as this increases, so as theta increases, right, W sub t is going to increase, right? And F sub r is going to keep increasing until it starts sliding down the hill, right? So as this increases, we're going to eventually get to a point where the static force, right, because we're going to have a frictional force that is working against the impending motion, right? The impending motion is going to be for it to move down the slope. But we've got a frictional force that's working against that. You know, it's going to keep increasing as W sub t keeps increasing until it reaches a maximum. And what is that maximum? That's what we want to look at. All right. And so if we redraw this in a free body diagram, we can see that we've got the frictional force working against the movement down the thing. We've got a tangential part of the force. We know that this angle here is theta, and we know that this angle here is also theta, right? So both of those two angles are theta. So we know that we also have a normal component of the weight force that's working perpendicular. I'm just going to extend this one back to the center of gravity here, the tangential weight force. And then we also know that opposing that, because it's not going into the thing at all, so there's no movement in that direction. So we know that opposing it is going to be an equal and opposite normal force, right? So what we want to do is we want to find out, well, where is that going to be? So the two opposing forces that we have here, right, for motion are going to be W sub t And we know, let's put a couple things here. We know that W sub t, right, is going to be the sine of theta. So it's going to be W times the sine of theta. And W sub n is going to be equal to W times the cosine of theta, right? Whatever W is. Okay? So that and we also know that this also equals n, doesn't it? Because if we have summation of forces in the y direction, W, there's only two, W sub n and n. So we know that that equals n. And we know that F sub r equals mu sub s times n. And that's n. So we know that F sub r equals mu sub s times W cosine theta, right? And so when we sum these two forces together, when we sum the forces in the x direction, we have, well, God, I better do it up here. Summing the forces in the x direction, just from our free body diagram that we've got here, right, equal to 0, is going to be the positive frictional force, mu sub s, times W cosine theta. And then it's also going to have the other minus W times the sine of theta. Does everyone see that? All right, so if we have this equation here, then of course what that implies is that I can take W out of both of those, or actually I can throw this one over on the other side, and that gives me, and W is going to come out of that anyway, but let's actually do it in a couple of steps. I don't want to lose anybody. So I've got mu sub s times W cosine theta equals W times the sine of theta. And then we lose W because it cancels out on both sides of the equation. And mu sub s, right, is going to equal sine of theta divided by the cosine of theta. Does everyone see that? Which, of course, equals the tangent of theta, right? So when the tangent of theta, so theta and mu sub s are connected. And here is our rule, is that theta equals the inverse tangent of mu sub s. So if I find out that mu sub s is 0.6, right, what would that be? Well, we know that 1 is going to be 45 degrees. So the inverse tangent of 0.6 is going to be less than that. In fact, it's going to be 30.96. And what did I say that was? It was the inverse tangent. I'm going to put a thing there. The inverse tangent of 0.6, because we used that in one of the last examples that we did, that was the coefficient of static friction. So this all seems to work out. So of course, degrees, 30.96 degrees is going to be the inverse tangent of 0.6. So if this thing had a static coefficient of 0.6, then I could only get this up to about 30.96. Now, what would be the angle of repose for aluminum on aluminum, and you have to go back to my last lecture in your notes to look at that, but that would be the inverse tangent of 1.35. And what was I saying? That if I had a powdered aluminum pile, right? Let's say that I had a powdered aluminum pile, right, that was all stacked up, right, on the table someplace, right? I'm drawing it in 3 dimensions. I don't know if you can see it, but what would that angle of the pile be? If this was aluminum, what would the angle on that pile be, right? That angle right there is the angle that I'm talking about, and it would be greater than 45 degrees. So the inverse tangent of 1.35 is 53.5 degrees, right? So this angle right here would be 53.5 degrees. I can't see that too well, maybe, but maybe you can. Yeah, I'm looking at it, and it looks pretty good. So I just wanted to point that out. We had some other ones here that were sort of high, steel on steel being 0.8. So that's going to be somewhere around 35 degrees, as you can see. But, you know, there's nothing that's infinity. Yes. Okay. Well, that was one thing that I wanted to look at today. And the other thing that I wanted to look at, besides the angle of repose, is the criteria for sliding or tipping. So let me just cut this off. Now, I'm not going to do an example of this. I don't really have enough room, for one thing, because I put that Christmas tree in there, that aluminum pile Christmas tree. But what I do want to do, though, is introduce. I want to introduce tipping and sliding. In fact, I can cut myself a little piece off here. Tipping versus sliding. And to talk about this and point this out, you know, and of course how it takes into consideration the frictional force, we have to think of like a filing cabinet. And I think everybody has sort of an intuitive understanding of moving a filing cabinet. You know, you've got to push down low if the filing cabinet is heavily weighted. Otherwise, at the bottom, let's say you've got the bottom of the filing cabinet's filled with files, and you start pushing on the top of the filing cabinet. Well, that's not going to work, is it? No, it is not. So what you have to do is you have to push low on the filing cabinet. Well, where does that, you know, stop? So let's just look at that for a second. Let's say that I've got a filing cabinet here, right? I'll make it a little bit higher. And I'm pushing on that filing cabinet, right, with a force P. Pushing on that filing cabinet with a force P. Now that filing cabinet, let's say that it's not got all of its weight at the bottom. Let's say that it's loaded from the bottom to the top with folders of equal size. So it has uniform density of weight throughout it. So it's going to have a weight force working downward, right? I think everybody can see that. And so that's going to then imply that there is a normal force working against that weight force that's going down. I'm going to say that if this is the carpet or whatever it is, the carpet or the floor, the linoleum floor, that this distance here is h. All right. And I'm going to say that the width, God, how can I draw this in here? The width of this is A. Okay. So then this would be A over 2, and this would be A over 2 as far as the weight force working down, right? And I would have, depending upon how high that would be, I would have a frictional force working against the impending motion, and the impending motion would be in that direction, wouldn't it? Because I'm trying to push it in that direction. So my frictional force is going to be working against that impending motion. I have my weight working down. I have my normal force working up, just like we've done in all of the schematics that we've had up until this point. So what are the things that are tending to rotate this about this corner over here, right? Because isn't that where the thing's going to rotate about? If I'm pushing a filing cabinet, let's call this a filing cabinet. If I'm pushing a filing cabinet and I'm pushing it too high, isn't it going to rotate about the opposite corner of the filing cabinet? Isn't that usually how it tips over? I mean, if we're going to tip over, I'm going to get a red pen here for a second. My tip over pen. Danger. Will Robinson. No. Yes. That dates me. Okay. So this is falling over and it's going to be rotating about that far corner, isn't it? That's right. So that's what we want to look at, is that right before this rolls over, what are the moments going to be on that point, about that point? Now, as I start pushing this, even if I push it low, doesn't it still tend to sort of like rotate a little bit about that? It's still, there's less force here and there's more force over here. So eventually, if I push it high enough, I'm going to force this figure right here, I'll call this figure 1. I'm going to force this figure 1 to look like this. Where I now have my normal force working right at that farthest point, right? Because I'm pushing it too high. That's my force P. There's my carpet. And here is my distance H from the ground up to P. And then what I've got is I've also got my my weight force here. And that weight force, of course, is A over 2 separated from this point. Why don't we call this point A? All right. So we've got point A right there. And then, also at that point, just before it tips over, so just before tipping, just before tipping, where is that going to be? Right? It's going to be right there, right before it tips over. All of my frictional force is going to be applied right at that point too, right? Because it's just about to tip over. I'm pushing it too high on a carpeted floor. the thing is going to, just tip over, isn't it? Do you see what I'm saying? Now, where is the difference between tipping and sliding, right? Okay, so let's look at the two forces that we have here on that one point. About this one point. Now, N is going through the point, so we don't have to worry about a moment through that N can cause. F sub r is going through that point, so we don't have to worry about any moment that it's going to cause about that point. We just have two moments. We have one moment, right, that's in the negative, so let's sum the moments about A equal to 0. We've got one that's a positive moment, and that would be W times A divided by 2, right? That would be the force, and it's separated from this by a distance, a perpendicular distance of A over 2. And that's a positive moment. Then we've also got P, which is a negative moment, right? And P is separated from the perpendicular of A by H. So what we have is PH equals WA over 2. So really, what we're seeing here is we've got two different forces opposing one another. We've got one that wants to tip it over, right? That's the tipper. And then we've got the other one that's holding it back down, that's trying to keep it, just sliding. So those are our two things. So we really are saying that pH has to be less than WA over 2. pH wants to tip it, right? WA over 2 wants to hold it down. I guess I didn't really have to write that. So H maximum, the highest that you can place force P on that filing cabinet, is going to be W times A divided by 2P, whatever the force is. Now let's look at that. So we've got WA over 2P. So if we know what the force is that we're going to push the thing with, right? That's going to, if I increase that force, that's going to decrease H max. But this really is the weight. It's really the weight to the force that you're pressing with, and then A over 2. So it's the, if I was to increase this, I could push it much higher, right? So in other words, if I had a much wider, like a desk or a table, if I increased A, but then we wouldn't really have slipping and tying. When have you ever pushed a table across the floor and had it flip over? Hardly ever, right? And of course, that's because A is so large. Also, if I had this that was like filled with gold bricks, if this was filled with gold bricks, then the weight would be super high, and I could use those. But anyway, I'll let you look at that, and that is the equation that allows you to decide. Now, I'm probably going to give you some homework problems that look at that too, the criterion between tipping and sliding, and I'll probably do a thing on it. Okay. I'm just seeing if I want to go on to centroids. I can't, let's just see. Yeah, I think I'm going to hold this lecture here. I'm going to probably do an example on tipping and sliding and a couple other things on friction too. But I think that I'm going to hold this lecture here before I get into centroids and centers of gravity, and then you know, things like mass moments of inertia and stuff like that. All right. So this lecture, and after this lecture, like I say, I think I'll do a couple example problems that really go over what it is that we've been talking about for the last couple lectures. All right. See you at the next lecture.